very much for offering me this opportunity. My handwriting may not be as clear as Maru's, so you might consider coming a little bit closer in case you want to be able to read what I write. I will talk about operads. Operads have occurred in this conference on several occasions, so I will not give the full definition. But just to emphasize a few things, these will be uncolored operads, or one-colored operads, or monochromatic operads, and I will use what is called a coordinate-free definition. So for me, an operad P is in particular a functor of finite sets and bijections. Okay? So an operad has P of A, any finite set A, and it has permutations of A and for bijections from one set to another act, and there is a composition operation which takes the form P of A times P of B. So you have an operation with A many inputs. You pick one input and you plug in an operation with B many inputs. So this gets you into the set A with the element A replaced by B. So this is a familiar notation from first order logic. So that's my notation for operand. So there is I want to discuss three examples. The first one is Cn, which is the operad of little n cubes. That's the mother of all operads, in a way. So I assume that you all know it. So, little n cubes. Cn of A is configurations of A-index families of cubes into the unit cube. And that's some conditions on these cubes. For example, the interiors have to be disjoint, the embedings have to be rectilinear. We will see a picture in a minute. I'm also assuming that most of you have seen this definition perhaps more often than they like. A second operad, which I will denote by Gn, is the operad of complete graphs, which was introduced by Clemens Berger. And Gn of A is complete graphs of A many vertices. So A is the set of vertices, and these graphs are directed. So just to emphasize, they're complete as undirected graphs, and then next you put the direction on each edge and weighted by the numbers 1 up to n. So every edge has a direction and a weight, which is a number between 1 and n. And these graphs form an operad because you can replace a vertex by another graph, and you do the obvious thing on the edges. But this is now a graph. This is an operad in topological spaces. This is a graph in posets. So an operad in posets. So I should tell you what the order is. So if you have two graphs on the set A of vertices, you say that G is less than or equal to H if the weights in G are less than or equal to H, and if the directions don't match, the weight has to really go down. Okay? So I will write this formally because it's important. If for any A and B in A, if in G it looks like this, you have the direction goes from A to B and the weight is I, then either A, J, B in H, and J is at least I, or possibly equal, or you invert the direction in H, but J has to be strictly bigger than I. Okay? And then there is one condition. So further condition, maybe I should have written it between the parentheses here. No cycles. Okay? So in fact, with these directions, you get a linear order on K. And then there is a slightly larger operand, G and next.
Sorry, what did you say this operator is called?
The complete graph operand. And this is the extended complete graph operand, which was subsequently introduced by Fiedorowicz, Vogt, and Brun, if I remember correctly. And everything is the same, except that there are no cycles of uniform weight. Okay, so that's a larger operand. So I would like to explain to you the proof, of the sketch at least, the proof of the theorem. These operads are all weakly equivalent. Okay, so you can understand what the method between operads and topological spaces. You have I denoted here P. So if you have two such guys, P and Q, you have a map from P of A to Q of A for every A, and it respects all the structure. Now we have operads and spaces and operads and posets. So the operads and posets you can view as operads in spaces by taking classifying space. Okay, so a common notation for this would be Cn is equivalent to Gn. So that's a geometric realization of the nerve. Okay. So there was some confusion about this theorem in the literature, on which I will not expand now, but I will sketch you a proof, which is new and hopefully correct. And the proof is based on the following diagram. So proof, like diagram. So the proof is by a diagram like this. So this is the configuration space of points. This is the configuration space of cubes. These are these graph operads. And so in particular, we have for every, and I will also put this on the board, we have for every A such a diagram. N of A, Gn of A, X, extended. Same names, pi, psi, inclusion. Let me also give this a name, gamma. So this is a category theory conference. So I have to warn you, there are all sorts of things wrong with this diagram. Okay? So it's a very hybrid diagram to begin with. Because this is an operad, well, this is an operad, this is a space, this is a poset, this is not, this is just a space, no? This is just, if you parameterize A, this is a symmetric sequence of spaces. This is an operative topological space, this is a operative process, this is an operative process. Moreover, this is an operad map. But this is not an operad map. Okay? And also the diagram does not commute. So what's this guy doing at the category theory conference? I will repair these things as we go along. And so maybe the first thing to say, I already wrote it, the fact that it doesn't commute is not too bad because it commutes up to equality, up to inequality. You have a question?
Yeah, can you elaborate on gamma?
Yes, I will.
Okay.
So it commutes up to equality, so it will commute, if you realize, it will commute up to homotopy. Okay? It commutes up to homotopy. The map phi, I will give you the definition of phi, that's important. So maybe I will do it here with the picture. So, if you have a configuration of cubes, for example like this, A, B, C, so the set capital A consists of 3 elements, then you send it to a graph on 3 vertices, A, B, C, and this is the first coordinate, this is the second coordinate. You look at the first coordinate by which you can separate the cubes. So for A and B, you cannot separate them by a vertical line, but you can separate them by a horizontal line, and then B is below A. So there will be an edge like this. Okay? For B and C, similarly, they're not separated in the first coordinate, but they are separated in the second coordinate, and C is below B. So we go like this. And then, if you compare A and C, then you can just about separate them in the first coordinate, and then A is to the left of C, so there will be an edge like this. Okay? So you see that you have a cycle, but not of uniform weight. There can never be a cycle of uniform weight, because the real line is linearly ordered. So that's the map phi. And for psi, you do something completely similar, but then you compare the position of points. Okay? If you have a configuration of points, you look at the first one, you pick 2 points, you look at the first coordinate that distinguishes them, and that's going to be the weight on your edge. So phi, this is the definition of phi, but phi is not a map of operads, because the operad structure here is going to substitute small cubes into larger cubes. So if I substitute small cubes inside B, then maybe these small cubes they lie here, and suddenly I can separate them along the vertical line. So it's a lax map of operads. Okay? Lax map of operads. Okay. So to make up for that, this is familiar to most of you, it's like replacing a lax functor by a zigzag of strict functors. Okay? So this is not serious. Not serious. But now this other thing, the hybrid nature of this square, because we have a space and a poset. What does this mean? Okay? So I'm going to, maybe I'll put that on another board, and so it's to leave it for you to look at. So if X is a space, and P is a poset, and I have a function, just a function of sets, okay, no conditional function, I can make a simplicial space xp, And the n sequences look like this. They are x, p0, pn, and x, f of x has to be less than or equal to p0. Okay? That's the nerve of a topological closure, if you think about it. So you can project to x. This is the geometric realization, or you can project to the nerve of P and realize it. So you get maps like this, and this map is always a weak equivalence. Okay? And this map is, I will use that, so let's call it pi for projection. So pi is a weak equivalence if each f inverse of down P, so all the x's that are below P0, for example, is a contractible CW complex. Okay? So this is how you can detect that a map from X to P is, quote unquote, a weak equivalence from X to the specifying space of P. Okay? So that's what I mean. Another way of saying it, we talked about these generalized maps in one of the lectures yesterday afternoon. You can think of such a thing as a generalized map in a homotopy category from X to the realization of P, because you go by a weak equivalence in the wrong direction and then by a true map. Okay. So that's the setting. Somebody asked me to explain gamma. So if there is if you have a configuration of cubes, you can take the centers of the cubes, you get a configuration of points. That's a map that goes the other way. But if you have a configuration of points, you can always draw sufficiently small cubes around the points. And that's maybe not very well defined as a map, but these two maps set up homotopy equivalence on the upper horizontal area in the square. So now let me try to. Okay, so now that I've said all that, it's enough to prove that psi is a weak equivalence. Right? Psi of A, for every set A, psi is a weak equivalence. So psi now is just a map from at A, this map here, is just a map from the space of a coset, and I'm going to use this machinery to prove its weak equivalence. And then on the right I have a map of Lex, be it the Lex map of operads. The gamma is a weak equivalence. I forgot to say, the map I, this is a weak equivalence. So I have to make a choice, and I will not explain the proof to you, but the proof is due to a student of mine, André Boytelman, and it's a very nice combinatorial graph theoretic proof. And we have a preprint, and you can read the proof there if you're interested. It doesn't require anything except some clever induction on these cycles in graphs. So I would like to focus on map psi. So the claim is that for every set A, the map psi is a weak equivalence. Okay? The proof of the claim will do this by induction on A. So I leave the case of the 1 point set to you, or maybe even the 1 point set to you, and so suppose A is B union 1 new element A. Okay? And then I'm going to draw a diagram of which at least one part should be familiar to you. So, just to repeat, this is a configuration of A many points. I forget one of these points and I get the configuration of B many points. Okay? And this is a very classical vibration, even a fiber bundle. It's Fiedorowicz vibration. Vibration. Okay, and you know what the fiber is, because if you fix a point here, so let me denote my B arrow, so that's a sequence of a B index, capital B index family of points in Rn, and you look at the fiber you still have to choose a position for this point A, and it has to stay away from these points in B. So if you think of the picture in the plane, so here are your points B, you just have to stay away from these 3 points. So what you get is really a batch of 3 circles. Okay, that's a very classical early 1960s paper. And maybe the first one. So this is vibration. So, and this is a weak equivalence by induction. So, if I can show that this is a vibration as well, and I can compare the fiber, and I have a weak equivalence at the level of the fiber, then I will have a weak equivalence here. Okay? So maybe the somewhat surprising thing is that this is also a vibration. Yeah? So, more precisely, after taking the realization, like here, you get a vibration, or what's sometimes called quasar vibration, or a vibration after homotopy. And the well-known criterion is if this is equivalence theory B. So phi is, or is vibration because it satisfies equivalent satisfies the conditions for equivalence theory B. Okay. Now, what are these conditions for equivalence theory B? If you have a vibration, the equivalence theory B does more. So, if you have a vibration, of course, the fibers have to be homotopy equivalent in the same path component. If you move from one point to another, the fiber can be homotopy. Type of the fiber cannot change. But it also identifies a fiber. But this is not. Sorry, this is not that. This is just a restriction. Okay, I call it rho restriction. There's nothing to do with phi psi. Phi psi up here. So this is psi. Sorry about that. So rho is information. So what this means is that i.e. rho over G, the slice category, does not change with B, with G, and is also a wedge of, well, in the magic n minus 1 spheres. Okay? And so you get if you take the fibers, then you have this wedge of spheres, and then you also have a wedge of spheres, and you get the equivalence here. So I have 3 more minutes. So let me indicate. So this is maybe a slightly surprising thing, but the argument is very nice for you. So let me explain to you for the case that you just have B consists of 2 elements. Okay. So I take a graph here of 2 elements. Okay? That's my B. And let's take n equals 2. And let's put 1 here. It doesn't matter what I put here. Then I have to choose my position for A. So A can be here, or A can be here, or A can be here. Okay? We're on G. So now linear orders. So if you are below one of these, like in this common category, rho over G, you put the maximum weight, which is 2. And you look at the things, at the downsets of these. And now I'm going to look at the intersections. Now what's the intersection between these two? Well, this arrow goes in the wrong direction, okay, compared to here. So if you're below both, you have to go down in weight, okay? So the intersection of this one is 1B0, 1B1, 2, down, union, B0, 1, B1, 1A, 2. And the intersection of these two is empty because you cannot go down further than 1. Okay? So you have two contractible pieces with the intersection consisting of two disjoint contractible pieces. So two contractible pieces that intersect in two disjoint contractible pieces, that's a circle. And with the intersection here, you get exactly the same thing. So that's a wedge of two circles. Okay? And it has nothing to do with this graph, except with the order between B0 and B1, which sort of determines the first circle and the second circle. So if you look at how this varies in G, it just pollutes the spheres. Okay? And that's a weak equivalence. So that's how you prove that this satisfies current B, and then it's very easy to compare the fibers using this criterion and finishes the proof. Thank you very much.
Thank you. We'll take one question.
So thanks very much. This is really interesting. Do you also have like combinatorial models for other well-known operads like E1, like little intervals or little bisque operads, or it's just little cubes right now?
Okay, so there is the notion of an EN operad. This preprint that I referred to with Boykomant is called a small catalog of EN operads. So an EN operad is one that is equivalent to the little n cubes. And so we have various other models. Well, we compare various other models that existed in the literature, I should say. I didn't come up with new models myself, but I did come up with some new comparisons. Okay? And the strange thing is that these EM operads play an enormously important role in homology, in topology, and in mathematical physics also because of possible brackets and high possible brackets and differential theory and so on. But there is no structural definition of an EM operad. And so an EM operad is one that is equivalent to one of the known EM operads. So that's very unsatisfactory. And this complete graph operad, this GN does seem to play a relatively central role, and its structure is quite simple. So maybe it gives a hint, eventually gives a hint to a structural definition of EN operad. But I have no answer to this question.
Thanks.
Thanks again.